So, continuing with the next part of our discussion on motion along a straight line or kinematics, we have constant acceleration topic. In the previous video, we talked about how the motion of an object, the type of motion that an object will experience, will depend upon the acceleration of the object. The object's acceleration might be constant or it might not be constant. In this video, we take a closer look at constant acceleration. We have two cases for constant acceleration. The acceleration may be constant at 0. You have uniform motion. For uniform motion, for acceleration constant at a 0 value, the velocity is constant. Acceleration is defined as rate of change of velocity. So if the acceleration is 0, the velocity is not changing. The rate of change of velocity is 0. That means the velocity is constant. And for constant velocity, v is just equal to change in position. So you have displacement delta x divided by delta t. Change in position divided by change in time. And the velocity is also equal to the average velocity of the object. On the other hand, when the acceleration of the object is constant at a non-zero value, the object is said to be undergoing uniform acceleration or uniformly accelerated motion. And for uniform acceleration, you have four equations by which you may analyze the system. V is equal to V naught plus AT, X is equal to V naught T plus 1/2 AT squared. V squared is equal to V naught squared plus 2AX. V average velocity is just equal to average of final velocity and initial velocity. So you have V plus V naught divided by 2. Average velocity is also equal to delta x divided by delta t. Consider now the following example. You have sample problem number 1. You have a car that accelerates from 40 kph to 100 kph, kilometers per hour, kph, in 10 seconds. Assuming that the car accelerated uniformly, determine the acceleration of the car. So here, the problem itself tells you that the object is undergoing uniform acceleration. And in fact, you are being asked for the acceleration of the object. So the car accelerated from 40 kph to 100 kph. Initial velocity is 40 kph. Convert to meters per second. The final velocity is 100 kph. Convert to meters per second. So final initial velocity 11.11111 and so on meters per second. And final velocity is 27.777 and so on meters per second. The elapsed time, the time of travel, is given to be 10 seconds. So t is equal to 10 seconds. Now, it's always good idea to convert your units to the MKS system, meter, kilogram, seconds. So, yung kilometers per hour, we converted to meters per second. So it's a good idea to do that so that during the analysis, during the solution, you won't have to stop to make conversions if needed because you have already done the conversion of the units. And sometimes stopping in the middle of your analysis just to do conversion of units will break the momentum of your analysis and you'll have a more difficult time finishing up the solution. Sometimes that happens. Of course, sometimes it doesn't, but to avoid that particular problem or difficulty, it's best that you convert the units at the beginning of your solution. So continuing with our answer, you're being asked to get the acceleration of the car, of the object. Uniform acceleration, you have 4 equations by which to analyze the problem. Again, going back to the previous slide, you have 4 equations to choose from. Say we look at the first equation, V is equal to V naught plus AT. V is equal to V naught plus AT. If you look at the known values, you know the initial velocity, you know the final velocity, you know the initial time. The only unknown is acceleration. So it's just a matter of isolating the acceleration A, plot in the values, and you'll be able to calculate that the acceleration of the car is 1.667 meters per second squared. Okay, so please be careful with your units. Acceleration unit is meters per second squared. Before we move on to the next sample problem, take note that here, we considered the initial velocity and final velocity to be positive. If you look at the problem does not mention any particular direction for the velocities. So, we can assume the direction of the velocities. And for our solution, we assumed the direction of the velocities to be positive direction. For instance, positive x direction. Our answer, A, is positive. This means that the acceleration is heading in the positive x direction. Moving on to the next example, you have sample problem 2. Starting from rest, a car travels 20 kilometers along a straight highway, so along a straight line, in 15 minutes. What is the final velocity of the car? So initial velocity, the problem tells you, starting from rest, that implies the initial velocity is 0. The car travels 20 kilometers, so distance traveled. Displacement, assuming to be positive direction. Again, the problem does not mention any particular direction for the motion of the object, so we assume positive direction for our solution. You may want to assume negative direction, but that adds negative signs to your solution. Since you are free to assume, let's assume that the direction of the motion is positive. Okay, now if the problem mentions a particular direction, you have to take into account that direction in your analysis. So assuming positive direction, displacement x is equal to positive 20 kilometers, convert to meters. Again, it's always a good idea to convert to MKS, meters, kilometers, kilograms are about that, seconds. So meters, kilograms, seconds. So in kilometers, we converted to meters, 20,000 meters. Time of travel given is 15 minutes, convert to seconds. 15 minutes is 900 seconds, and we are being asked to get the final velocity. Clearly, the car moved. It traveled 20 kilometers. So even though its initial velocity is 0, for it to travel 20 kilometers, the velocity of the object must change. So there is rate of change of velocity, there is acceleration of the object. And you have final velocity that may be different from the initial velocity because there is rate of change of velocity. Now, the question is this uniform acceleration or is this non-uniform acceleration? As mentioned in the previous video, for non-uniform acceleration problem, the problem will typically give you an equation that will describe the motion of the object. Here, the problem does not give you an equation describing the motion of the object. So we can assume that this is uniform acceleration. Uniform acceleration, you have 4 equations to choose from. In the previous problem, we chose the first equation in the list. Going back again to a previous slide. In the first sample problem, we used V is equal to V naught plus AT. For this sample problem, let's take a look at the second equation. X is equal to V naught T plus 1/2 AT squared. Initial velocity is 0, so we can cancel out V naught. X is just equal to 1/2 AT squared. We know X. We know T, time T. The only unknown is A. We can isolate A. A is equal to 2x over T squared. Plotting in the values, we are able to get A to be 0.04938271605 meters per second squared. We got an answer, but that's not the answer that we are looking for. We are looking for final velocity. So we are not yet finished with our solution. Using now the equation that we used in the first sample problem, V is equal to V naught plus AT. We know V naught. V naught is equal to 0. So V, final velocity, is just equal to AT. We know time, 900 seconds. We have just calculated the acceleration, so we know A. We can now calculate the final velocity. So plot in the known values, the known and the calculated values. We are able to get the final velocity to be 44.4444 and so on meters per second. So final velocity is equal to 44.444 meters per second or 160.000 kilometers per hour. Next, we have the following problem. Sample problem 3. A man sees a car without a driver roll by, and he starts sprinting after the car at a constant speed of 3 meters per second. The car has an initial speed of 5 meters per second and is decelerating at a constant rate of 0.5 meters per second squared. How long before the man catches up with the car? In the previous two examples, you only have one object that is moving. In this problem, we have two objects to take note of, the man and the car. For problems with more than one objects that are moving, say, like in this example, two objects that are moving, don't make it more complicated than it is. Don't make your analysis more complicated than it is. What you do is, you analyze the motion of each object separately. Analyze the motion of object 1 separately as if object 2 does not exist. Analyze the motion of object 2 separately as if object 1 does not exist. And then, you combine the two analyses using either time t or displacement x. In many problems that involve more than one object, the motion of the objects are either related by time or they are related by displacement. So, doesn't matter if you analyze the motion of the object separately, you can later on unite the two analyses using either time t or displacement x, as you will see in this example. So, the man has a constant velocity of 3 meters per second, whereas the car has an initial speed of 5 meters per second. So, initial velocity of the car, 5 meters per second. Now, once again, the problem does not specify any direction for the motion of our objects. So, we can assume that the direction of motion is positive. So, velocity of the man is positive, initial velocity of the car is positive. The problem tells us that the car is decelerating at a constant rate of 0.5 meters per second. We assume the direction to be positive, the direction of motion to be positive. Deceleration, the object's acceleration is heading in the opposite direction as the motion. The motion is positive direction, therefore the acceleration of the car is in the negative direction. So, negative 0.5 meters per second squared. And the problem tells us that is constant. So, the car is undergoing uniform acceleration, whereas the man, constant velocity, the man is undergoing uniform motion. So, if you analyze the motion of the man, use uniform motion analysis. If you analyze the motion of the car, use uniform acceleration analysis. The man catches up with the car, so the displacement of the man is just the same as the displacement of the car. Let the displacement simply be x. The time of travel of the man is the same as the time of travel of the car. So, let time of travel be just equal to t. And that is what is being asked for by the problem. How long before the man catches up with the car? So, analyze the motion of the object separately. Analyze the motion of the man separate from the motion of the car. So, starting with the motion of the man, constant velocity, uniform motion. There's only one equation for uniform motion. Velocity is equal to x over t. X, therefore, is equal to velocity of the man times time t. So, this is what we got by analyzing the motion of the man. Let's now analyze the motion of the car. The car is undergoing uniform acceleration. You have 4 equations to analyze the motion of the car. One equation is x is equal to initial velocity of the car times time plus 1/2 acceleration of the car times t squared. X, we can unite our two analyses using x. So, V man t is just equal to V car 1t plus 1/2 A car t squared. We can cancel out t, which will give you V man is equal to V car 1 plus 1/2 A car t. No, t squared. So, if you divide by t squared will give you t. We are looking for time t, so isolating time t, we get an equation with all the known values. We know y man, we know x man, sorry about that. No, v, sorry about that. V man, we know v car 1, we know a car. Plotting in the values, we are able to calculate the time of travel. 8.000 seconds. So again, when faced with a problem that has more than one objects moving in the system, just analyze the motion of the objects separately, and then later on you can unite the different analyses using either time t or displacement x. And that's it for now. That's it for this video. In the next video, we'll continue our discussion of motion along a straight line. In this video, we covered uniform acceleration. In the next video, we'll take a look at non-uniform acceleration. So, thank you for watching.